Swayam Prabha. Digital India. Educated India.
Is based out of figure 2-15. Let me pull that up. You used 2-7 yesterday, but let's just quickly go over some of the options you have available. Okay. So this was the CR values that you can use, and then the one you used yesterday was positive shockwave parameters for spherical TNT. So spherical TNT is air burst, equivalent to air burst. Now don't ask me what if it is not at sea level. I can't produce those graphs or what it is inside. It's got to do something with the pressures, ambient pressures. I'm sure that's the reason. Okay, you're calculating negatives from here. Then the reflection that I talked about today, variation of reflected pressure. Now in a wall, you might say, okay, the height of the building is, let's say this is a 10-story building, that's 100 feet. And the top need not be designed. You can decide up to what point you need to design for blast resistance, maybe the lower level alone, and the upper levels you don't have to. So that's a decision you can make and say, using angle of incidence up to the second floor, what are the pressures? Second floor design can be different from the other floors. So that's why this could be useful. Then this is reflected, again, impulse and pressures. Then we looked at this. Scale triple point, we talked about it. Surface. Now surface burst, this is the most common aggressor tactic. And so from here on, the curve that is utilized for all your designs and my example today is figure 2-15. And I think your afternoon example also is going to be based on that. So once again, notice this is PR, then PS. So it's an order here, I think. Then IR, then IS here. So the scaled values are all given as divided by W power 1/3. So the only thing that is not scaled is the U, PSO, basically the wave speed, and the pressures are not scaled. All the others are scaled. So that's one way to recognize. And then the last, and so the order is actually not quite. So here it is T naught. This graph could be a little better, but maybe they had symbols, it would have been nice. But this is the one we would be using today. So let's take up an example and we'll draw some correspondence in both. So let's say you have a building. As I mentioned, this would be part of what you'd be doing this afternoon as well. And so you have the dimensions that are given are, this is 30 feet and 12 feet. And that seems to be very low, but that's okay for this example. And this is height is 11 feet. So let's say this is the height, this is the width B or W, this is your L. And so it's on the ground, blast, standoff distance is R, which is 100 feet. And the TNT value I have chosen is 800 pounds. So you have your front, side, wall, roof, and the rear. Questions is, determine the following. The P versus T curve for front wall, the roof, not necessarily in that order, I don't know which way I'm presenting, but side walls, basically the front part. So the side wall is this part of it, and the rear wall. And please ask any questions at any point. Hopefully I'll be able to answer all of them. If I don't have an answer, Ralph, ask him. He probably knows better by now. Or Kavir. So important figures I use are this is all from UFC 340-02, figure 2.3, 2.196, 2.197, 2.198, 2-15. These are some, and I'll bring those references as we go along. So first step, these are all optional step. First step is, let me start with optional, because no engineer is a good engineer unless they add their own conservatism to what the problem statement is. I'm sure civil engineers would have heard of the bicycle joke, right? Is it okay to crack? You haven't heard of that? No? You want to hear it again? So I was in the government too, right? In the government, the ranks are the people at the site, junior engineer on the site, then there's the assistant engineer, superintending engineer, then the chief engineer, right? And so the design goes, JE does as per drawing. Oh, everything is set. You know now the story. What does the assistant engineer do? Add one more rebar. SE adds another rebar. CE adds another rebar, right? They don't feel good unless you're adding conservatism. And actually, there is a truth behind this. I'll tell you that also. And then chief engineer leaves, the bar goes, and the drawing comes back to the original one. So the truth behind this is in ACI 318. They recognize this, whatever you're doing, over reinforcing the structure, correct? That's not good. What does over reinforcing do? Total failures. So they enforce ductility in various ways. I think maybe IS 456 also does that in some way, but especially since I think 19 or 14, 318, for the last 10 years, the code that's applicable in the last 10 years, the ductility is enforced with strain limits, and there's several ways they enforce that. So there is, that's when I thought there's perhaps truth to that story all over the world. So optional, we increase weight, whatever you feel good. So I feel good at 20%. So anyway, I say that because these calculations would be haywire. You'd have to help me calculate if I don't have that number. So we'll go with 20%. And interestingly, in my class, I do this, I mention it, and then they come and ask me, how about if I, 1.3, can I do 1.2, 1.1? And I laugh. I said it is optional and your choice. So, and then you've gone through this. That's why I set up the tutorial yesterday, so that it's not something you have seen, but you've actually had a chance to go through yourself. So this is figure 2-50. Again, this is ground. It's not ground shock. I should say that a better term is surface air burst versus surface burst. So start with Z, which is your R divided by cube root. This afternoon, I was talking with Professor Aragapan, and the same problem. I think instead of doing yourself, since there's so many references to be done, we thought we might pair you up and you can do the tutorials this afternoon. I think you'll still get the same out of it because there's a lot more work involved. So this is 100 feet divided by cube root of 960 pounds. And so this Z value is 10.13 feet per. Again, this value is far range. In fact, I mentioned yesterday Z less than 0 to 3 is near range. There is a further classification. We go actually from 0 to 0.3. I'll mention it again. It's actually close in range, and then the Z of 0.136 you have seen, right? That was another reason to mention that. So some of it is close range, and then the reason that is brought out is applicability. We are given something, we assume it's applicable for everything, right? That's the tendency of human mind. But the applicability, always every equation is only good as its dash. Not silence. Every equation is good. What did I say? Every equation is only good as its assumptions, right? Yeah. So he's finished his PhD. So you see motivation to do PhD, you get depth of understanding a subject. Only good. We always forget that. You start with even basic equations. They start with assumptions. State, nice equation. Assumptions are into the dustbin, and it becomes a black box. So be careful of that. Mindful of what. Look for it. If you don't have to know the assumptions. If not, investigate. Even the parameters I mentioned this morning, all those complex equations, and if you see some of those parameters goes into 4 decimals, right? Investigate what are all. That's the first thing I always look at. Interpolation is always better. It's the right. It works for interpolation. Anything you're extrapolating, you're kind of on your own. So I can pull that, for example. Let's just have a look at it so that you're familiar with it. So if you see, I don't think I can write, but Z is, no, what do I have? Okay, Z is somewhere here. So you have your side-on pressures somewhere in PSOZ of 10. It comes somewhere here. So all those values are along. I picked that 960 basically close to be equal to 10 so that it's easy for. I solve problems that are easier to interpret. Your problems may be more involved numerically. But so the side-on pressure, PSO, if you have any questions, please ask. But I'm going to just write all the values for it. The third thing is your arrival time, these are calculated from the taken from the graph. So arrival time cube root of W. So this is 4. So this gives me arrival time of 4 multiplied by cube root of 960, which is now this number is in milliseconds. So 395 milliseconds. Fourth one is the blast. Let's put this as one word. Blast wavelength, LW by cube root of W is 2.4. Again, these could be subjective, as you have seen yesterday. This could be a range, not subjective, but they're definitely a range. So LW is 2.4 cube root of 960, which comes to 23.7 feet. And this brings an interesting question, right? It's 23.7 is not that high. The length of the wall, I think somebody was asking this question for the rear wall loading. And then the load duration, T naught by cube root of W is 2.7. So T naught is 2.7 cube root of 960. The units are in milliseconds. And I don't think we'll need it, but we'll pull out all the parameters. And incident impulse IS by cube root of W is 8. So IS itself is 78.9. So this is another thing I keep in mind. It's always better to use numbers. It's easier to say 7 kilopascal versus 0.007 megapascals, right? So convert anything into numbers, that makes it easier. So milliseconds is a better unit, although I wouldn't say that it's wrong to use seconds. And finally, the reflected pressure. And I can use the reflected pressure, use 2-15, since the angle of incidence alpha is 0. Otherwise, use the chart that you have. And so you have PR is 25 psi. There is no need to if you use just as a reference, if you use, if 2-193 is used, what you have is for PSO is equal to 9 psi and alpha equal to 0, you get CR is about 2.6, or PR is equal to CR PSO, which is 2.6 multiplied by 9, which is, so keeping these two not that far apart, you can use whichever is right. So any questions on this part? And let's anyway go ahead and calculate all the values here from the graph. The final one is the reflected impulse. All from 215. So IR by cube root of W is 18, or IR equal to 177.56 milliseconds. So let's gather up all the important values. What we have here is PSO is 9. If you can maybe read out, PSO is 9 psi. PR was how much? 25. 25. Then load duration TD was 26.6 milliseconds. Blast, these all of these are needed. How much was this? 23.7 feet. And incident impulse is 78.9 psi milliseconds. Also get familiar with numbers, used to numbers. Incident reflected impulse is 170. I like to gather all these at the end because it gives me sort of a sanity check, making sure numbers are where they should be. LW is smaller than what I would expect, but anyway. And then arrival time is 39.5 milliseconds. So the next step, which is 3, is when I'm in class, the biggest corrections I get, it's step 3, not step 4. I've written step 4. So people are paying attention to the steps, but I don't know, hopefully they're paying attention to details. And I find that always hilarious. Front wall positive phase pressures. So if I make mistake in my step number, please do feel to correct me. We start with the clearing time. The clearing time equations are different for both the scenarios, the petrochemical facilities, and here the equation TC is 4S divided by 1 plus R CR, or 4S divided by 1 plus R is S over G multiplied by CR. Go back. Okay, so this is 1 plus S over G CR, and as we had seen earlier, CR is the reflected pressure region sound velocity. Or sound speed. And this comes from figure 2-192. And that figure is the one that did not. So here you see in terms of PSO, this is figure 2-192. So it's based on PSO. And so from that figure, you should be able to get CR, we said, is between 1 and 2. So CR No, I'm sorry, CR is the velocity itself. Still shows up. It is 1.28. The units are feet per milliseconds. So be careful of that, or 1280 feet per second. So PSO was 9, and S is the lesser minimum of W by 2 or H. So here, if you look at it, it is either 30 by 2 or 11. B is 30. So this is minimum of 30 by 2 or 11. So S is equal to 11. And G is the max of either W by 2 or H. So this is max of 30 by 2 or 11. So which is 15 feet. Let me change one thing. I might make a quick change because I don't want to change my calculations here. So let's make this change to 40. So this is 40 by 2 or 11. So this comes to 20. And so therefore, I can calculate TC to be 4 times 11 divided by 1 plus 11 over 20 multiplied by 1.28 feet per millisecond. So this is feet out here, comes to. So TC is 22.1 milliseconds. Then IS, that's why we need this impulse. So this is 177 point. Now here you have incident impulse and the reflected impulse. So TOF, let me look at this. I think I might need. So TOF is calculated this way. I have to check on this. I'm a little doubtful, but let's go with it for now. I'm going to confirm it with you. So this is 2II divided by PSO. Yeah, you can use with PSO. Since we're using it with PSO, you can use that. So this comes to 2 times 78.9 psi millisecond divided by 9 psi. So TOF comes to 17.53 milliseconds. Then the third parameter to calculate is the dynamic pressure. And this comes from figure 2-3. So I had mentioned earlier the different figures that we are using. 2-3 was one of them. So figure 2-3, let's get familiar with that now that we are done with it. This one. So figure 2-3 is 10, 9, 8, 7, 6. So here is 2-3 peak. Based on PSO, you get the peak dynamic pressure, particle velocity. Again, this is something I had shown yesterday. So the peak dynamic pressure is figure 2-. From this figure, you get Q naught directly is 1.8 psi. And the peak pressure now is with CD equal to 1 for front wall. We can write PSO plus CD times Q naught is 9 plus 1 times 1.8. This is for PSO. So so this is the peak, again, blast pressure or blast wind pressure. We'll see where this comes into play. So let's call this PSOF. Or I don't think that's an appropriate terminology because this is more related to Q. I'm trying to make up a terminology here. So let's say Q peak. So Q peak is equal to, and then we calculate the equivalent triangular loading. This is for the reflected pressure. The reflected pressure, we have no modifications for that. Now we have seen that this is TR, this is duration. So TR is 2 times the reflected impulse divided by PR. So this is 2 times 177.56 milliseconds divided by 25 psi. So this comes to TR is 14.2 milliseconds. So the positive part of the loading looks like this. You have your PR, which is 25 psi. Then you have the QP, which is 10.8, so roughly half of it. And it is coming down to 14.2 is 1, and TOF is 17.53. So this curve goes in this manner. This curve goes in this manner. So the net loading is for the positive phase. Your impulse is going to be, and TC we calculated how much? So TC is, now you might find this situation, right? What's the problem with TC in this calculation? It's more than TOF. So Yeah, that's a question I get, and I don't know if I have a good answer for that. Um, but one way, if you were to calculate, so let me make a note of it. TC calculated is how much again? 22.1 is greater than TOF. So for the purposes, um, so for design calcs, um, calculate TC from the graph, or determine, I should say, determine TC from the graph. I don't have a better answer for that. Maybe I should investigate into that. It's also got to do with the building size and height and all that. Our building is pretty unusual in size, so that's also plays a role. So let's call this step 3A for positive phase, and let's say this is step 3B. Now we calculate the negative phase parameters. Okay. Any questions? How you've worked out the homework? I mean, the not the homework, the tutorial, right? So, anything you see, all of them, fine. Okay. Any comments or good? Okay. Yeah, very grateful to Rauf, and he's working out a lot of all the. I'm just reading out numbers in the tutorials, but he and Raghav, they're all working together to put this all together. So for the negative phase parameters, what you need is PR is 25 psi and IR is 177.5 psi millisecond, and alpha is equal to 0. Now here for the negative phase, it's a little interesting. If you go back to this figure 2-15, so we have to calculate the negative pressure PR alpha. So in order to do this, let me see what I did. Yeah. So if you go to figure 2-16, yeah. So here you use the negative shockwave parameters 2-16. So scale is 10.13 somewhere here. And from this, the PR negative is, this is the PR negative. So PR, this seems to be the PR negative value. And that value comes to around, so and somewhere here, 1, 2, 3, somewhere around that, right? So from figure 2-16, PR alpha negative is, let's say, 3 or 3.1. I have it as 3.1 psi. And so therefore, I can calculate the duration TRF negative. I didn't quite show you this part of it in my earlier explanation, but it's the same process. TRF negative is 2 IR alpha negative impulse divided by PR alpha negative. The IR alpha negative can also be calculated. If you see here, you have IR alpha negative. So for 10, roughly, it is divided by W1 power 3 comes to 10 point something. Let's say, so no, this is 10, 20. So 20, let's say roughly around 70. So for this, we need negative alpha. Again, figure 2-16 for Z equal to 10.13 feet. You have IR alpha negative divided by cube root of W is, I have it as 17. So therefore, IR alpha negative is 17 multiplied by is 108.2 milliseconds. Sorry, 167.7. So from this, now we can calculate TR alpha negative is 2 times 167.7 psi divided by 3.1. This value is 108.2. So that's one. Then other time parameters. There are 3 other time parameters. One is 0.25 TR negative. Alpha is 0. So this is 0.25 times 108.2, which is 27 milliseconds. This is again sort of the rise time. And then T naught plus 0.25, so comes to 53.6. And T naught plus TR alpha negative is 26.6 plus 108.2, which is, so these are the different time parameters. And so that would go back, I should have plotted this later on, but if you go back here, we are starting T naught is how much? 26.6. So this is 17.53. And then it goes to not much, 53.6. So 53.6 and 134, let's assume it's a broken scale, 134.8, and peak is 3.1. this value is. So that would be the solution for the front wall. So positive phase, let me make sure we have all the numbers in. 25 psi, 10.8, 14.2, 17.53, 26.6, 53.6, 134.8, 3.1 psi, I think, matches with. So keep in mind, this is PSO plus CD Q naught, the drag coefficient. So that's your front wall loading diagram. So you can change that. I don't know what the numbers are, but anyway, let me make a note. It's not going to make much difference, but better to time calculations. Surprising, I never noted it till now. It's 0.27. Well, you learn something every day. Correct yourself. Okay, so which step are we in? 3B. So now we go to step 4. It's like, I don't know if it happens here. If I give a bonus homework and they don't submit, they worry. They come at me. They submit the bonus homework, but not the actual one. They'll come back to me saying, I've submitted the bonus. Why didn't I get points for it? Well, I give them the points, but the irony of it is kind of lost sometimes. So, step 4, let's look at the sidewall pressures. Now, in the sidewall, again, this is a choice this afternoon you can make based on whatever you feel comfortable or whatever you want to do, or you can try a couple of different things and see how it makes a difference. So this is 12 feet, and I'm considering a sidewall, the first half of the sidewall of 6 feet. It also depends, on your structure, right? If you have columns, you can consider the first panel and then use that. So consider 6 feet wide sidewall, giving L is equal to 6 feet. Second thing is the blast wave arrives at the same time as front wall. And the third one is, okay, those are the two assumptions. So first part is we calculate the CE, LWF by L, basically the wavefront length That's a better way to call this rather than the blast wavelength, wavefront length divided by the wall length. So we said this is L1. And so here it is 23.7 divided by 6. And so if you go to figure 2-196, so this is 215. Let me go down a little. I've copied this figure in the main. So this is a velocity sound, 2192, then 3, 4, 5, there's still 4, 5, and 6. So here you have, if you see, positive CE and negative CE for a given value of LWF by L. Okay. So let's be consistent with the terms. LWF divided by L is 3.95, and so for 3.95, let's say 4. Now you'll find that the values are sometimes off the charts, especially for the negative. It stops right here. Positive, you're able to get something for 4, which is this line. So for 4, you're able to get somewhere between 0.8 and 0.9, a little above that also. And whereas here it stops at about 0.2 something, 0.28 or 0.275, whatever. So from you'll find those scenarios happening as well in this. You don't have a choice. So from this graph, I get CE positive is 0.88, CE negative is 0.28, and I choose not to extrapolate. So that's extrapolation could be problematic. There is a reason, and I don't know why they stopped at that point. So don't extrapolate. All these graphs just stop at the max value. Let me make a note. Use max value or min if out of range. And then the second is from 2-197. I think it's the end of the page. So from 2-197, which is basically the rise time for uniform pressures. So the scaled rise time is what we are calculating here. So from 2-197, you get TD over cube root of W, and it is as a function of LWF by L. So the same thing is used. So for LWF by L equal to 3.95, TD by cube root of W is 1. So TD is 9.86. I don't think it's advisable or wise to go to second digits beyond the decimal in this case. And then you go to 2-198. Scaled duration, you get TOF from this graph. So third thing is scaled durations TOF plus and TOF minus. TOF is by cube root, again that's used here also. Cube root of W is 2.5, so TOF is, so multiply these both, you get 24.7 milliseconds. Then the dynamic pressure, again that would change. You use figure 2-3, and from here you'd get Q naught is, it's not very different, but you get Q naught is 1.6 psi. So the max blast wind pressure, which is CE times PSO plus CD Q naught, is 0.88 multiplied by 9 plus, now here the drag on all is minus 0.4 multiplied by 1.6. Then the negative pressures, with the same thing, CE negative is 0.28. So PR minus is CE minus multiplied by PSO, which is 0.28 multiplied by 9, not PR, the maximum here, which is 2.52 psi. We use PSO because it's a sidewall. Then TOF for LWF by L equal to 3.95, TOF negative by cube root of W. The same thing for the scaled, so I get this to be 10, or TOF negative is 98.64 psi. So this is, and so the time parameters, milliseconds, correct. Thank you. So time parameters are, I'm going to go with 0.27. It's going to be a little different. So I'm using 0.25. So this comes to 26 milliseconds. Then TOF negative plus T naught is, what did we calculate? 98.54 plus 26.6, which is 127.2, and T naught plus 0.25 TOF negative is 52.6. So the graph here is .28 psi and at 9.86, coming down to 24.7 and then starts at 26.6, goes to 52.6 that we just saw, ends at 127.2, and this value is 2. Here the impulse, I mean, it's lasting, it's a small pressure, but you can calculate the impulse is still fairly significant. Let me do the roof at the end. Because the roof is very similar, just keeping time in mind, let me make a note of it. Roof loading. Here, the procedure, if I finish a little early, I'll complete this, is very similar to sidewalk. Choice to be made is for LWF. LW. I considered the whole 12 feet roof. That's the roof. Again, as I said, if there are joists, you can break it up. So whatever you choose, you can work with it, but the process is exactly the same. I don't see anything different. Because I'd like to finish the rear wall and also show you comparisons. We may have time, so I'll come back to that. But any questions? Now, the rear wall load, now here the main difference is R is now 100 plus 12 feet. I don't know, I think I made a calculation mistake in my case. Doesn't matter, we can go back. If somebody has a calculator, you can, anybody has a calculator? Okay, so yeah, we can help me with these numbers. We'll redo these calculations. I've got it as 30 feet for some reason, which is not right. Okay, so Z is, you have R divided by cube root of 960, which is 112 divided by cube root of 960. So, how much? 11.35. So, going back to our parameters, so keep some numbers in mind. So how much was it? 11.35. So roughly, it's not going to be very different. 12. So PR is the top curve, roughly somewhere here. Let me call it at about between 10 and 20. It is closer to 20. Let's say 3/4. So let's say PR is, so from 2-15, we have PR, let's say 18 psi. PSO, how much was it again? 11.35. 11.3, maybe it's a little overestimated. So PSO is right here, about 5 psi. Let's say a little over 5. Let's say 6 psi. Let's use. And LW by cube root of W is, which is the blue line here. So this is about 13, between 2 and 3, closer to let's say 2.75 or 2.8. Say this is 2.8. So LW, if you can help me with this, 2.8 multiplied by cube root of 960 is 20. Say 27.64 feet. Thank you. Then we find the LWF by L. So which is, again, hold that number please, 27.64 divided by the length. L is so in the back wall, L is the back wall height. I didn't mention that, so note that. L is the wall height, so this is 11 feet. So how much would that be? 2.51. Then go further down. For LW by L equal to 2.51 and PSO equal to 6 psi. Then going back to two point 196. I don't know if you have that with you. Let's see. Okay, we are close. So 287, 2.194. Yeah. So here, this is roof. So from figure 296, you get CE plus, and how much was LW by L? 2 point. So CE negative is still 0.28, and 2.51, this leads to about 0.7475, you can say. Yeah. So this is L, yeah, wavelength is LW, span length is L. So wavelength is 23.7, span length is 11. So what was the mistake, you think? Wait, wavelength is how much? Yeah, divided by span length is 11. So it's 5. No, I don't think so. Is anybody? So here, if you see, this is wavelength divided by span length. Wavelength is 23.7, span is 11. Zoom what? Yeah. Oh, you can, this part. So, yeah. Okay, so 2.51. So, let's say in this case, CE plus is from 2.196, CE plus is 0.74, CE minus is 0.28, again not extrapolated. And from 2-197, TD by cube root of W is for, this is 2.5, so it's way beyond. And next to numbers indicate the peak incident overpressure. So incident overpressure is how much? 6, you said 6? 6 psi. So somewhere in between. So let's say this is 1.4 maybe, let's say. Shall we go with 1.4? So between 1 and 2, closer maybe 1.3 or 1.4. So let's say 1.4. So TD is 1.4. I had 1.4, so. But yeah. Then go to 2-198, TOF positive by cube root of W, TOF negative divided by cube root of W. So negative pressures and positive pressures you can calculate from here. So this is 2.51, again it is beyond. And based on the pressures, the positive, now the negative pressure, for positive pressure we are calculating, how much is PSO? 6. So 2, 4, 6, somewhere in between. So it's between 3 and 4, right? Somewhere here. And the negative pressure is this line. So this line stops at 10, maybe 11. So what did we say here? 3.5, let's say. So this is 3.5 and this is 11. So help me with this. TOF plus is 3.5 cube root of 960. TOF negative is 11. What are those numbers? 34.5. Okay. And? Okay, thank you. And then we calculate the dynamic pressure Q naught. This is figure 2-3. And Q naught, figure 2-3 going back. Yeah. This is 2987655. 4, and 3. So this is based on an incident pressure was how much? 6. So 6 right here, and we get this to be about 1.7 plus 0.7. It's divided into 3 parts. So roughly, let's say 0.75 maybe. So this is 0.75 psi. Then the maximum, again, I'll need your help, is CE PSO plus CD Q naught. So which is 0.74 multiplied by, I think you said 6 psi, plus minus 0.4 multiplied by 4 point. And same thing, the negative pressures, just go a little over today. So the negative pressures is CE minus PSO, which is 0.28 multiplied by 6. I don't have this number. 1.68. So what we now have, TO by cube root of W. This is the duration. Is different now. This is again from figure 2-15. For Z was, what was Z? 11.35. Coming back here, figure 2-15. So for Z equal to 11.35 and T, what would you say it is? This one is roughly 3, right? So let's go with 3. So this is 3. So T naught is equal to 3 square root of 960 cube root. And if you calculate that, now T naught plus 0.5 TOF negative. How much is this? 29.6. So this is 29.6 plus 0.25, then multiplied by, we calculated that to be 108.5. And T naught plus TOF negative is 29.6 plus. So when you get me those, it's going to be, I'm not including the arrival time. You can include that for design purposes. I mean, you can show that. So the peak values were negative 1.68 psi, and the peak positive was how much was it? 4.2, you said? 4.14. T naught was 29.6. And so the other numbers, I think this was, I don't know what these numbers were. So 138.1. And these two were, I think, 26 something. Professor Hargapan, can we go another 5-10 minutes? Okay. Okay. So what were those two? $13.8 and 34.5, right? No, 13.8 and 34.5. So I don't know this number 20. So this seems to be a little off. It has to go in there. 34 point. So the number, it should actually go down a little like this. So the overlapping sometimes it's okay. So this is your so next little bit is what I'd call as bonus, just comparisons. Comparison with the equations. We had given W was 960 pounds, Z was 10.13, PSO was 9, TA was 4 milliseconds, TD was 39.5 milliseconds. Then PR was 25 psi. LW was 23.7 or 237. I don't know. 27.6 LW blast for the first set, not the one for the back wall, for the front. 7. Yeah, I have to check if that was a mathematical. Seems low. Would have expected 237, but 23.7 feet. What am I missing? What is U? And Q naught was 1.8 psi. So these were. Did we calculate U there? I think we did, right? Last wave, the speed. And then the other parameters were H equal to L, which was 12 feet, W equal to 30 feet. Sorry, L was 12 feet and H is 11 feet. So, 40. Yep. So, coming to the front wall, we can do a couple of them and check. These are easy calculations. PR is 2 plus 0.05 PSO multiplied by PSO, which is 2 plus 0.05 multiplied by 9. I have calculated these out. So this is, you can check though, 22 psi. Then S is the minimum of H or B by 2, which is the minimum of either 11 or 40 by 2. And the clearing time, the equation here is different. And we can compare this clearing time. So, in fact, this will be higher if you see. This is 3S divided by U. What was U? Did anybody get that number? Wave speed? We can go back and check. So the LW, we didn't calculate U, right? So U, I think I had an expression. Let me check. U is, so U, and help me with this, please, 1130 multiplied by 1 plus 0.058 PSO power half. So this is 1130 multiplied by 1 plus 0.058 multiplied by 9. One. So 1394 feet per second. So you get TC, and again, please help here. 3 times S is 11 feet divided by 1394. How much was this? 0.02 seconds or 20 milliseconds. And this would fit in well with the previous one. Remember, TC was going out. So, and you can calculate graphs where it meets and compare. You know, these are interesting things you can try yourself. That's what I would do. 23 seconds? Oh, okay. So 23 milliseconds. So in this case, the drag coefficient CD equal to 1. And so PS, the stagnation pressure, is PSO plus CD Q naught, which is 9 plus 1 times 1.8, which is 10.8 psi. So you calculate your IW, which is 1/2 PR, which is 25, minus PS, which is 10.8, multiplied by TC, equal to, TC is 23. So basically this is 25 minus 10.8 multiplied by 23 plus 1/2 of the P R the maximum pressure we calculated was 10.8. So P max multiplied by TD. So this is 1/2. The max pressure we calculated was 22. No, not that. This one, 10.8. So 10.8 multiplied by TD was 39.5. How much was, yeah. You can put these numbers separately and add them up. How much? So the effective time is 2 times IW divided by PR. So 2 times 376.6 divided by PR is 25, 22. Oh, 22. So this should have been 22. It's okay. Don't change it now. That's fine. That'll lower it. So let's say 22. Or you can change it if you. So this comes to 30. And we've seen how the front wall loading looks. So if you compare some of these, the PS is 10.8. Front wall loading, we have that. PR was 22. This was 25. The effective was, how much did you said just now? 24.34. And TOF was the so here you see it looks different, right? Maybe I think we'll continue later on the other part.